So today we'll do some more of Gaussian processes, as in we'll wrap up Gaussian process regression and classification. And these are actually some of the most effective and powerful tools for basically doing nonlinear, non-parametric classification and regression, unless you want to use considerably more fancy techniques. Before I go into detail, two things. First of all, are there any questions from last Monday? Okay. Who thinks I'm going too slowly? Okay, no hand goes up. Who thinks I'm going too fast? Okay. Okay, so therefore, by exclusion, since nobody raised a hand in either way, it means I must be going just at the right speed. So, if you think otherwise, let me know in the lecture, not in the forums. That's kind of lame. Okay, guys, if I'm going too fast, let me know here, not afterwards online. Everybody can be here online. I mean, you can tell me after the class and say, Alex, you're going too fast and I didn't understand this and that. So, ask me in class, because then if I answer your question, I might answer a lot of other people's questions too. So you're helping your fellow students if you ask questions, guys. So do ask. Okay. Next question. Oh, okay, cool. Question. Great.
Slides. For one of them, it said red slides.
Yes.
You can fall asleep, but they might on the exam. Is that the case for all red slides?
Okay, so here's the thing. If I were to make everything green, it would be kind of pointless. So the green slides are the things that you really, really should remember, and I hope that even in a year or two, you'll still remember at least vaguely what was on the green slides. The red slides, maybe you'll remember that there were some of those, and you'll be able to look them up later on in a year or two. I mean, I can make my life very easy by just only talking about the green stuff, right? It's easy. I have to prepare a few slides, and I can go very slowly through it and do things in the blackboard. But then you're not going to learn that much. So to some extent, what this lecture, like with any other class, what it does is it explains to you the basic concepts. It also shows you more detailed specific solutions or detailed specific techniques that of course you're not all going to remember for the rest of your life, but you'll remember well enough that they existed, that if you ever had to go back at it, you could probably look it up and then use them for specific solutions. And you won't believe how useful sometimes your lecture notes and slides are. So I just had a situation where I lost some lecture notes from 20 years ago, and I sent the professor who taught the class an email and said, well, can I have those lecture notes again? And he's retired in his 80s, and he actually scanned it and emailed it to me, which was really awesome. I don't know whether I'll have my slides from 20 years ago anymore at some point, but so don't underestimate how useful this stuff might be even a long time from now. And this is why you should at least remember that there was something along those lines on some slides at some point. For the purpose of the exam, you need to know a little bit more than that. Okay, so in terms of midterm exam, you can bring as much paper as you want. Okay. So the index has to be built in your head. Okay, so that clearly tells you that there's an optimal amount of paper, right? Because if you bring an entire library and you don't know where the stuff is, you're still screwed. The answers to the questions will not be found in the handout by just looking at the notes and copying stuff down. I mean, that would be too easy, right? However, obviously having the lecture notes will help you. However, what's not cool is if you bring your phone or your laptop or your iPad or any other electronic device and Google the solution. So some of the questions that will show up will probably be related to things that people actually care about. Right? If it were something really cool and unrelated to anything that people would have done, we would probably go and sit down and write the paper, and sometimes stuff like that happens. So this is why you can actually expect that things are related to the lectures understanding the lectures, understanding some of the derivations actually will help. So it's a good idea if you know how convex programming works and how you set up those optimization problems, right? It's going to be a good idea if you know what model complexity is, right? It's a good idea if you know that random variables converge. It's a good idea if you understand how kernels work, right? This is definitely a good idea, and it's going to be a good idea not just for the midterm, but a good idea for also research. I mean, after all, this class, I mean, there's a reason why you're supposed to take it, right? And the reason is that it's supposed to help you with your research, right? So that's why essentially expect the most important things of what we've been teaching to be more likely to show up in the exam. But of course, it's not only going to be the green slides, right? That would be too easy. Okay, good. So with that out of the way, I mean, Barnabas will be there when the exam is held because I'll actually be away. Are there any other questions? Cool, thanks.
So can we have the current slides posted on?
They will go online, and I'll put them online as soon as I'm done with this slide deck. Just haven't had a chance yet to correct all the typos. The videos are already online. The easiest way to find the videos is to look at my 701 playlist on YouTube. All the videos that I upload go on there. I'm not quite sure. Barnabas seems to be having some technical difficulties with some parts, but my slides always, my videos immediately will go there within probably about 12 hours of the class. So I upload it usually in the afternoon, and then it takes some time until Google gets all the processing done. Because, yeah, unfortunately, we're not as popular as Justin Bieber. So maybe fortunately, anyway. Any scientific questions about last Monday? Okay, cool. Then I'm assuming everything's clear and well understood, but let's just refresh a few things. So remember we talked about this weird beast called Gaussian processes. And they were given by basically an index set, where I evaluate things on, and then, a mean and a covariance function. And this is the second most trivial version of a Gaussian process, because the most trivial one would be where my index set is just one, has just one entry. So, single Gaussian random variable with mean and variance is, of course, a Gaussian process. Now, here we have a Gaussian process with, two entries in the index set, namely height and weight, as in, the symbolic entries, height, and symbolic entry weight. And then what I do is, I get, the joint distribution over values for height and weight. And then reading that off, I can do inference like, given that this person is that tall, well, what's he going to weigh? That's what happens if you go to the doctor and he tells you, well, I've got to lose some pounds. Yeah. So more generally, we have this expression here. And just to make things really clear, those T's and mu's are vectors in their own right, and those K's are matrices, right? So then they could be just scalars, but they in general will be vectors. And so we don't just divide by a number, we invert the matrix, and that's why you have to be a little bit careful whether you put that inverse to the left or to the right hand side. So that's about the only thing that you need to worry about. Yeah, so that's what we already saw from last time. Is everybody okay with that expression here? So that's probably a fairly nasty looking thing, and you would have probably wanted to invert that matrix at some point in your life. I think it's good practice to do also for next week. Okay, so then we have the linear Gaussian process, and we saw that, okay, things can go horribly wrong here, namely our predictive uncertainty can decrease to 0. That's like saying, well, I've already, I know that my, observation space is, let's say, 10-dimensional, and I've already made 15 observations, so then I've completely pinned down any future observation that I might have. And that's of course, completely being supremely overconfident in your own abilities, and that doesn't work very well. So if you have something like this, so you get this flat pancake shaped, distribution, or figure or whatever, then this is probably not going to work so well. So what we made as an assumption is that we have direct access to those variables t, and then, well, what we say is, yeah, actually maybe, this is not really what we observe, but, our observations are slightly noisy. So we know that reality is really that low dimensional, but hey, we pretend that whatever we observe is maybe not quite so consistent with reality. So we basically observe a noisy version thereof. And what this did is it fattened up the covariance matrix. So this is what you got, right? So we had this mean covariance, and we derived that this is the Gaussian process in the y's that you get out of it. And we basically solved an integral without even trying by just arguing, means and covariances for the sum of the random variables. Because we knew that sums of Gaussians are Gaussians again. By the way, products of Gaussians are not Gaussians, right? So just be careful of that. But sums are. Okay. So this is what we had. So then it's actually really straightforward, because now you just plug this equation into this expression here, and you can do regression. Because we have, the means, the covariance matrix. Okay, so now this is the data. These are basically our t's. And what we want to do is we want to find out, the distribution of a t prime given t. And I'm cheating a little bit here because I'm saying, well, we observe those, I guess these are probably about 15 points or so. And I want to estimate t prime for a one-dimensional t prime given all the rest. That's actually not really what I should be doing. I should be looking at the joint distribution over all those t primes. But for computational convenience, I'm cheating a little bit, just looking at each of those means separately. Okay, that's what you get. It looks quite reasonable. And then, so by the way, this is the equation that you code up, as you would have already seen. And then this is the uncertainty, and again, I'm basically asking, what's the uncertainty at that point, given what I've already observed, rather than the joint uncertainty. And that makes a lot of sense, because it's very unlikely that you'll have one observation here and one there. So, both might be here or both might be there, so they might be correlated. But just for a single observation, given everything else, of course, that's the uncertainty band that you get. So the green dotted lines are just mean plus minus the variance. The red line is the variance. An interesting thing that you can see here is that the variance increases here and it goes up there. And it also never gets really, really small. Okay. Why does the variance increase over here and also a little bit over there? Exactly. So we have that's exactly the right answer. We have no observations here. So therefore, there's basically no evidence over here further to the right that would help us pin down these observations. Okay? That would also explain this bump here. Now, there we have a lot of observations, right? Why does it not decrease any further? Exactly, sigma squared. So basically what happens is that we assume that we have the covariance from our Gaussian process for the unobserved t's, and then we have additive Gaussian noise. And that additive Gaussian noise will never go away. So even if I observe, at the same location 100 times, each of them is going to be independently noisy with, sigma squared. So this gives us a natural noise floor below which we can never go. Okay, very good. So that's what explains those two effects. Now, does it matter which function values I observe here? I mean, or does it just matter where I observe the values? Okay, who votes for just where it, who votes for location and who votes for value? Who votes for value? Who votes for location? Okay, who votes for both? Okay, so the correct answer is location and location only. Here's why. Because in this Gaussian process, we essentially pre-specified already the entire noise model. So now, given that, it doesn't really matter what we observe at this location, because we know that, condition of the observations, everything is still Gaussian. Now, this is obviously wrong, right? This is a stupid assumption to make in reality, but it's a very useful stupid assumption. But it's only useful if your assumption about the Gaussian process is not too horribly, out of sync with reality. But if you have a reasonable assumption of, what correlates and how, then this assumption is okay. But, just be aware of this. And there are ways how to fix this. For instance, you can design heteroscedastic Gaussian processes, and they basically would go and estimate at the same time the mean and the variance based on a somewhat more complicated inference problem. Then you cannot integrate out the latent variables anymore entirely, and the math becomes a lot more fun. So that would actually go and fix this. But that's a lot more complex. Okay, so just for reference, this is actually what generated the data. This was this blue curve. This was basically just a sine function. And yeah, I mean, you can immediately see, yeah, this is doing the right thing. So it stays reasonably well within this predictive uncertainty. Partially also because I used the right additive noise. Okay. So here's just as a refresher the ugly details. This is exactly what you saw before. I'm just explicitly instantiating where you add the diagonal correction. So this equation I've shown you, this is now the 4th time. So if you're counting equations, this doesn't count. That's the same equation as before. But what happens here is, for this covariance matrix, you now add on the main diagonal sigma squared. Here again, for this covariance matrix, you add on the main diagonal sigma squared. That's the same matrix. Okay, trick question. Why don't I have to add sigma squared here? This is the off-diagonal block, right? It doesn't have any diagonal entries, so it wouldn't fit anywhere. Basically, this is really, if you think about it, let's look at our matrix. This is K, T, T. This is K, T prime, T prime. This is K, T, T prime. This is K, T prime, T, which is exactly that one transposed. So the things that I'm adding is here on the main diagonal, the correction. That's why it works. And this also makes sure that the matrix always retains full rank. Okay. Any questions about this? I mean, this is basically what you implement. Here's the pseudocode. So just in case you are really worried about implementing this, I mean, the only thing that I didn't instantiate is how you get this kernel function. So I'm assuming I have some function here. And this is an inefficient implementation of what you would do. So basically, here what I did is I really just computed, this part. and I've just divided by this matrix. As already explained, a smarter idea is to factorize this matrix KTR into two Cholesky factors, so LL transposed, and then divide by one and then divide by the other. And well, then for prediction, this is what you get, and likewise here for just the predictive uncertainty. So this is easy to code up, right? It's 4 lines of MATLAB code. Well, 3 lines in your editor with a smaller font size. Okay. Any questions about that pseudocode? So, I mean, it's sufficiently simple that you can, I remember at the time when the handspring visor was a cool device. This is like a long time ago when Palm Pilots and so on were still cool. This was a cheap clone of it. It had a MATLAB emulator. So I had Gaussian processes running on my handspring visor. And this was literally like 6-7 lines of code. And you wouldn't have wanted to type more because you had to type it in with a stylus. Okay, so now the last thing that I want to do to wrap a Gaussian process regression is to connect this to support vector machines. Because we've now had kernels occurring in at least 3 places, and I already told you Parson Windows kernels and SVM kernels are not the same thing, but SVM kernels and GP kernels are the same thing. So remember, Gaussian process that we've been playing with all the time now is given by this mean and some covariance. Now let's just pretend that we build some linear model in feature space, so T of x, so this would be another approach, is phi of x dot w plus mu of x. Okay, I can always do that, right? And I'm assuming that this w is normally distributed with 0 mean and unit variance, or covariance in this case. These are vectors. So I can immediately see that T of x has to be normally distributed because, well, it's a linear combination of random variables that are normal, so therefore it has to be normal, right? And it also has a mean. The mean is mu of x, right? Because this has 0 mean, so therefore this thing also has 0 mean. So, now we have something where, each of those T of x's is normal. We also know that, an entire vector of those guys has to be jointly normal. So we know it's a Gaussian process, right? Because for any such vector, it's going to be jointly normal, so this is okay, and we already worked out the mean function. The only thing that's missing now to specify it entirely is the covariance function. So let's just, write it out. Well, this is the expectation over W of, the covariance between T of x and T of x prime. I've already subtracted the mean because otherwise the equation keeps missing. Okay. So can anybody explain the step from here to there for me? And for the rest of the class? Any volunteer? What's going on between here and there? Because this is like this big messy beast, and here it looks really simple. Yep. Correct. So the proof strategy is you pull the phi of x's out of the expectation. This is exactly the right answer. So you basically use the fact that the expectation over phi of x of w phi of x, and we're taking the expectation with respect to w, is the same thing as phi of x transposed expectation of w transposed phi of x, right? Prime. Okay. Now we all know what that thing is, right? This is the identity matrix. It's the identity matrix. Why? Because, well, we made it so. Because we said W has to be zero mean unit variance. So you know, we have complete control over it. So this is the identity. And something multiplied by the identity, well, is whatever we have before. So this is nothing else than phi of x transposed phi of x prime. Okay, and that's our kernel. If you had realized that connection about 15 years ago, you would have managed to write a very highly cited paper. It's a nice result by Chris Williams. And the embarrassing thing to everybody else around that time, including me, was that we didn't see this. It's super embarrassing. In hindsight, it's so obvious, right? These two lines. So you can see how slowly science moves at some point. But yeah, it's quite beautiful. Yeah. Any real mathematician would be laughing about this. But yeah, this is machine learning. Okay, so here's what we have. So Gaussian process, we have latent variables drawn from a GP. The observations are t, but corrupted with noise. And so what happens is that the original covariance just gets that covariance with, you know, something added on the main diagonal. And then you get this atrocious math for, you know, solving for the mean and covariance. And there are three things that you can do about this. One is you memorize the equation. The other thing is you make sure you can rederive it by inverting that one block of the covariance matrix. The third thing is you figure out some URL where you can always look it up. No, actually, there's a fourth version is you buy Lutke Pohl's book, which by now, unfortunately, is a ridiculous $140. But this has everything you never wanted to know about matrices in it. I'm open to suggestions 5, 6, and 7. I know none of them is particularly fun, but, well, it's just how life is. Questions? And yeah, this is essentially what runs in a lot of support vector, in a lot of regression packages. And then the entire beauty of it is, and the entire game is, how do I make this go really fast? Because right now it's ridiculously slow. This is cubic. You can essentially reduce it to something that will have more or less linear runtime. And that's where a lot of the research in the past 10, 15 years went. Okay, good. So now let's move on to something slightly more complex, classification. Okay? It's recording this slide and that slide. It's recording both. And yes, okay, I mean, you'll have to probably squint or use a big display. But there'll be the slides available as well. Okay, so, yeah. And maybe it might be recording my head. Okay. So, Gaussian process classification. Well, let's do something very simple, right? So in regression, let's just compare, how we actually solve the regression problem. We said, we have x, and then, we had this, Gaussian process that indexed the t's, and then the observations y were really just the t's with some noise added. And then we managed to solve this integral so beautifully without actually ever noticing that we solve an integral, and everything was fine. But the connection was really this function here, right? P of y given t, which was, this function there. It's just a Gaussian, right? It's just additive noise. Bad noise with, variance sigma squared. Okay, so now let's say we have y's being plus minus 1s. And I can still play the very same game. So I just use, t is normally distributed with some mean and covariance. But now, of course, I need to get, ones and zeros or plus minus 1s out of this. So I could, for instance, use this logistic function. So what I'm going to do is I'm going to use 1 over 1 plus e to the minus yi/ti. This looks a little bit bizarre. Why on earth do I pick exactly that function? Why is that reasonable? But we'll actually see a little bit later today, or then possibly after the midterm, why this is reasonable. Okay. So, so far I can do that, and you can check for yourself that if you, plug in values for 1 and -1, these numbers add up to 1. Okay? Everybody's okay with that conceptual part, because that's actually the hardest bit of the entire Gaussian process classification part. The rest is just math, but this is the hardest part conceptually. So we now have latent variables, which are scalars, some numbers, and we have observations, which are plus and minus ones. And I want to match up those scalars with those plus minus ones. Later on, the things that we have here to match up might be entire sequences of bits. They might be, integers of some range. They might be ratings if I want to do, collaborative filtering. They might be, I don't know, segmentations of an image, right? So those y's later on are going to be, whatever objects you encounter in reality. And those t's are going to be things that you can easily treat on your computer and optimize over and so on. And it's essentially up to this link function here that links the things that you can easily deal with the things that you observe. And this is the first example of a non-trivial link that doesn't just go away by some mathematical massaging. Any questions about this so far? Okay, good. Here it is, the logistic function, right? You can see 0 for a long time, and then it keeps on increasing. At some point it's 1. Within that range, it's more or less linear, but then it just asymptotes out. And you've probably seen this before. Okay, so for regression, well, we managed to integrate out those t's. We got rid of them, so this was nice. For classification, well, it's not so nice because, well, we can't really solve this integral. So what we can do is we can write p of t given y and x, and you get this entire expression by base rule. So we get the distribution over the t's given the y's for some training data. Now, what you really should be doing is this following thing, right? So because we want to predict for some new y primes, what they are, we want to get their distribution. We have the observations, we have the labels y, and we have the covariates x and x prime. So these are sets, right? So so there's obviously a slight notational inconvenience here. This means really integrate over t and t prime. So dt and dt prime. So you basically have to integrate over, let's say I have 1,000 training points and 500 test points. I have to integrate over this 1,500 dimensional space of now p of y prime given t prime. Okay, in this case I know neither y nor t, y prime nor t prime, times p of y given t, at least I know the y's, times p of t and t prime given x and x prime. So what this already tells you is that effectively if you were to do this, you would be able to address a lot of things that have special names. Like one of those names is transduction. Within transduction you're basically given both, so to say, the lecture notes and the exam questions. So think of t prime as think of x prime as the exam questions. Think of y prime as the answers for the exam questions. Think of y as the answers for the homework, and think of x as the homework and then the lecture notes and whatever. Right. So of course if I were to give you the exam questions today, you could do a way better job at getting the exam right than you would be if you were given the exam just at the time of the midterm, right? The latter is standard, estimation where you have a training set, and the training in your case means, well, you study, and then you have a test set, which is you show up in the exam and you do the best you can. And most likely you're not going to do much training at test time. At least I hope that you'll have done the preparation before. Yeah. But reality sometimes isn't quite that mean to us, right? So we might have actually the test questions at training time. And so you could actually solve this entire thing. The only thing is there is no closed form solution. And if you wanted to solve this by Markov chain Monte Carlo, you'll need a big machine and wait for a long time. But you could do that, and in some cases, I mean, there are papers which show that if you're willing to do this, or come up with a lot of really clever approximations, this actually works really nicely. And mind you, the other parameter that we didn't really adjust yet is how to choose the kernel, and so on. So if you were to do all of this, you'd actually get a really, really nice estimator. But this would be something like applied probabilistic modeling, and it would not be a 701 class. This would be quite a bit beyond that. This is where people still write papers about. So how do we hack it? And this hack is pretty good. It's good enough that we can get away with it. So the first thing we do is, well, we say, hey, rather than integrating over the t, well, we just find the maximum of this expression here. So p of y given t times p of t given x. Okay, I can always do that, right? Because I can write that integrand as, well, p of y prime given t prime times p of t prime given t x and x prime times, well, p of y given t times p of t given x. And of course I have to do the integral dt prime. Now the horrible approximation that I'm going to make is this one here. I'm going to replace this guy here by delta t and this t hat max. So in other words, I'm going to replace something that actually would be a distribution over different values by just, point mass. That's horribly wrong, but in practice it works reasonably well. It works reasonably well, especially when that distribution has only a single mode, and then you can actually quantify how things go. And that actually turns out to be a nice convex optimization problem, and I'll show you how to solve it on the next slide. Of course, it completely ignores the correlation in the test data, so this is really bad. Then you go and find t prime as the argmax of p of t hat given t prime, give p of t hat and t prime given x and x prime. So that's another approximation here, right? We are going to then just zoom in on this block. So this is block number 1, this is block number 2. And we find p of t prime given t hat. And only then we deal with the poor y primes given t primes, and we'll just say, hey, this is from a logistic. So as you can immediately see, we started out with a problem that's very beautiful and nice and principled and all. And in order to then to solve it, we made a really horrible mess out of it. And that sort of kept researchers busy for at least the past 10-15 years, how to make a less horrible mess out of it, or how to prove that this mess isn't actually that bad. Well, which is fun, at least gives people something to do. So here's what we do. The first thing is p of t given y and x. Well, that's up to the normalization constant, the prior in t. That comes from our Gaussian process, and I've set mu equals 0. Is everybody okay with where this equation where this part came from? This is really that term here. That's where this comes from. And then we have here the log of 1 plus e to the minus yi. Well, that's this term here. We have just m of those guys. And we've taken the log, and since we need to do the argmax, we might as well minimize the negative log, and so there's an optimization problem. I think it's very obvious that it's convex in T for the first term. For the second term, well, you need to squint at it and, maybe plot that function. And actually, we've seen those functions before because we've seen a logistic before. Remember? The logistic looked like so. And this is proved by crappy drawing that it's convex. Okay. So then, after you've found T, you can find T prime by just doing the map estimate. And of course, you would go and pre-compute this yellow bit again. So same trick as before for regression. Then you have the covariance matrix and you get the T primes. And then and only then you can say, okay, now I'm ready to actually estimate the P of y prime given T prime. So what this will almost certainly do is it'll underestimate the uncertainty you have in y prime given T prime. Okay. So remember, this is an approximation. It's a pretty good one. It works really well in practice, but it's still an approximation. And that means that occasionally you'll find a case where it doesn't work. Okay?
So here, how we get the covariance matrix, we just redefine it?
Yes. So just as before, we just make one up.
So we have actually non-truncated non-parameter into averages.
So, okay. So basically, this is actually a very good question. Where does our prior come from? Where do the priors come from? They come from our idea of how we believe the world ought to be. Now, in some cases you get lucky and you have access to some other related data, some other related information, and you can use that to make a more informed choice of picking a prior. But you might just squint at the data and say, hey, this is really good. Okay, this is my prior, right? You can do that. There are actually slightly better ways of doing this. So the slightly better way is, well, if you think about it, we have P of, y prime really, given T prime, P of y given T, P of, in this case, T prime, given x prime, and k. K is, for instance, our kernel in this case. And now what's missing from this is we also have a P of k given some other parameters, let's call them eta. So this thing is called a hyperprior. Hyperpriors are extremely useful. They're extremely useful because they are usually more diffuse, less specific than a prior, and it lets us essentially find a good prior from a family of priors. So for instance, you might say, okay, I have radial basis functions, covariance function, Gaussian RBF kernel, but I really have not the foggiest idea what the bandwidth should be. So I could say, hey, well, look, this is a reasonable number for the bandwidth, but I'm not quite sure. Maybe it's twice as large, maybe it's half as large. So you make some prior on the bandwidth, which effectively acts as a hyperprior on your prior. The problem is that you then need to solve the integral dt prime, dt, and dk, right? So you've just added one more variable to that entire mess. This can be done. It's just not trivial. Which is why initially when people started doing this,
should this be the eta?
What?
Should this at the master should be the eta? I mean
okay, so good question. So why don't I integrate out over eta? You could. You could have a hyper prior, right? And you could continue this ad infinitum. The problem is at some point it boils down to you as the engineer or as the as the scientist making a bet on what do I expect to see. And it turns out that there are significant gains by having a prior on your prior, in other words, by having a hyperprior. And there are very insignificant gains, unless you've been very stupid, by having a hyper-hyperprior. On top of that, it just gets really expensive computationally, so people usually don't do it. So usually you stop at the hyper. Okay, good. But this was a very good question. Yep.
Can we set pre-specify a candidate set for the priors and then pick up the best one from?
You could do that. So let's say I have, maybe 15 different bandwidths of maybe I have 15 different kernels that I like, and I think it's going to be one of them. Okay. So here's a simple. So basically, let's say we have kernels K1 up to K15. And so I want to have what I want to have is K is drawn from some distribution P of K. Okay. So the easiest way would be to have P of Ki is just 1 over 15. Okay, I could do that. That would be a flat prior over this. But maybe I like this K1 twice as much as all the others, right? So then I would have, P of K1 is 1 over 8, and P of Ki is 1 over 16 for all I greater than 1. You could do that. And once we're at that, why not have a continuous distribution? So there's nothing to prevent you from going fancy on this. By the way, the same mechanism exists for structural risk minimization. So the stuff that Barnabas was talking about. Because there, as well, you need to specify a hypothesis class, right? So we talked about VC dimension. And there are many things that have, many function classes that have a specific VC dimension, right? So if you've already had a look at the homework, you would see that there are some function classes that have a high VC dimension, but they look really simple in the other way around. And actually, this tells you something already intuitively, that maybe this sine AX function isn't for arbitrary a isn't a very good parameterization to solve a problem, because these functions intuitively feel really wrong, and they give you these pathological outcomes, and this is probably not something you want to have in reality. So, in a way, by designing a set of function classes with increasing VC dimension, you are already effectively, specifying, well, what it amounts to here a prior. And just like here, imposing that all those probabilities sum up to 1, you actually end up, because you'll end up taking a union bound over the various events of, solution this and that and that and that class, you also need to make sure that the probabilities over those classes sum up to 1. So you have exactly the same effect. It's the same mechanism underlying it, just that the mathematical tools afterwards to treat it look very different. So there are some tools that tie those two together. So the Pack Bayesian bounds, so David McAllister started with them, are probably some of the earliest instances thereof, or also if you prove Chernoff bounds in some ways. But this explains a little bit why you pay a price for being too general. Okay. That's a very good question. Any other questions? Okay, good. So let's look at a few free pictures, right? So clean data does what you would expect, except that now these boundaries aren't really the margins anymore, but I just picked some lines. I think they were probably around, probability, 1/4 and 3/4. And a noisy data, well, it does something reasonable too. So the only thing is you don't really have support vectors anymore, but arguably it produces a slightly more visually pleasing solution. And in terms of actual performance, it works as well, in some cases slightly better, in some cases slightly worse than an SVM. So let's just revisit the connection to SVMs. Basically, in the SVM, what we had is we had minimize 1/2 alpha transpose K alpha, plus, and then I've just, rolled the soft margin loss function into the objective, the max of 0 and 1 minus this, so this is the margin. This would be basically instantiating the representer theorem, plugging in the alphas directly and solving the problem, the primal, which sometimes can be a very effective thing to do. And then if we, on the other hand, we look at our logistic regression objective for map estimation, we have something that looks very different, right? Neither the first nor the second term really match. Remember we had, going back, we had this problem here. It's the same equation, so it doesn't count as extra equations, right? So we had 1/2 T transpose K inverse T, plus and then the logistic term. Now let's reparameterize things. This was the other thing that Chris Williams did in his 98 paper. He said, well, let's pick alpha equals K inverse T. And if you do that and just plug it in here, well, what do you get? Well, you get alpha transpose K alpha. Bingo, same term as here. And now, rather than the soft margin loss, we have the logistic loss. So this, by the way, means, well, matrix vector product in the ith entry. And if you look at this picture that you've seen before, it's very clear why those things actually behave very similar, because, well, the blue curve is the, well, logistic. The green one is the soft margin, and the red one is the Hooperized soft margin. If you use VW, for instance, Walpole-Wabbit, you get the red line. If you use an SVM like LibLinear, you get the green line. If you use a GP classification package, you get the blue line. And so all the difference is just what happens, around the margin. And there are some cases where one works better than the other. And to my knowledge, there's no really definite answer about which one works better in general. As a rule of thumb, if you have very low noise data, then the SVM will do extremely well. If you have fairly noisy data, the logistic will do really well. Okay. And this sums up Gaussian process classification. So basically what we did is we looked at latent variables drawn from a GP, the observation drawn from a logistic model, and then we just happily went on our merry ways and optimized by doing a couple of really horrible hacks on the way by essentially replacing integrals by maximization. And the reason why you can get away with that, as you probably recall from before, is if I have a distribution that looks like so, then if I integrate over, let's say this is a random variable x, if I have to solve the integral dx, that's approximately equal, basically, just x, it's approximately equal f of x hat. Now these things go horribly wrong if you have to follow anything. First of all, which x hat to pick isn't so clear anymore, especially if the problem now is not convex. You might not actually find the true mode. On top of that, if I just want to solve the integral and I pick the wrong, then the mean is probably going to be somewhere around here. But if I pick the mode, it's going to be really horribly bad. I can make it arbitrarily. I can design distributions that are arbitrarily bad for map estimate. So that's why you actually need to be careful here. Okay. So this
is a Gaussian distribution.
So for a Gaussian, everything is nice and convex. And that's good news, because that means we're in this situation. Right? Because if I have a log concave distribution, it has a single mode at most. It can never have more than one mode. Okay. Any questions? Good. then let's do a bit of exponential families. Yep. So we have this zoo of distributions that you've come across, and of course, can we do anything meaningful with it? So, right, here's the slightly less fun version of that. Okay, so this is stuff you should remember, remember really well. So this is like bright green. Okay, so we have distributions P of x parameterized by some parameters theta, which can be written as e to the inner product between some phi of x and theta minus g of theta. And this g of theta is the normalization. And I'll show you in a moment how you get there. But just meditate on that first line. So this is really just e to some linear function on the features of the data and with some parameter. And this gives you an enormous expressive power in terms of what distributions you can model. As a matter of fact, if you stick an arbitrary function in here, you can model any distribution. I mean, that should be obvious, right? So I just take a log of whatever density I have, and I stick that in that exponential, and I'm done. And then I just say, hey, well, that's an element in some Hilbert space or some Banach space at least, and I, use the inner products, and bingo, I'm done. So that's kind of beyond the point, and the math gets extremely unpleasant computationally if you did exactly what I suggested. But nonetheless, there are a lot of cases where people 100 years ago solved the integrals for us. We're not going to do anything that requires you solving any integral specifically beyond what's already been done a century ago. So don't be scared. And they didn't have MATLAB and Mathematica and Maple. So how do we get this normalization G? Let's just start with, P of x parameterized by theta is e to the phi of x of theta minus some constant c. And that constant c, of course, will need to be chosen in such a way that the integral dx of P of x parameterized by theta equals 1. Right? So from that it follows, because we have a minus c here, that c equals the log of the integral dx e to the, now I have this phi of x of theta. I just took the logs of that outside the integral. See, before that I had basically e to the c standing here, but this is not so scary. And now that's exactly what our function g of theta does. So this is really just, going through the definition. The thing that is a lot less trivial, but you should remember it and remember it really well, is this thing here. That the derivative of this function gives you the expected values and also the variances. And I'm going to derive that for you in the next slide. Now, quick question. So assuming that, these two equations are true, which we are going to check on the next slide, but assuming that the second derivative of g of theta gives me the covariance of phi of x, then why does this immediately imply that g is convex? Exactly. So this just checks that the second derivative essentially is greater or equal than 0, and second derivatives in d dimensions give me matrices, and then checking greater or equal than 0 means checking that all the eigenvalues are greater or equal than 0. And since we know that covariances can never ever be negative whatsoever, we therefore know that this must be a convex function. This gives rise to a lot of beautiful math, and you can write a lot of papers about that. It's really pretty math, but we're not going to go into that in a lot of detail. However, we're going to exploit that connection between mainly the fact that you have a derivative and that you have an expectation here. We're going to exploit that over and over again. Because in some cases, we may choose to be very lazy and not really try to explicitly compute expectations, and we'll just take derivatives. And that gives us interesting optimization problems. In some other cases, we may not be able to ever get our hands on G directly at all, because it'll turn out to be NP hard to compute and all that. However, we may be able to estimate its derivatives. It's kind of a crazy thing, right? Where you can't really get your hands on the function, but you can estimate the value of the derivative. And in those cases, you can manipulate those derivatives in such a way to adjust the parameters for inference and so on better. So that'll become more clear as we do graphical models, but this is already a bit of a heads up that we'll be playing on that, you know, on those two aspects. In one case, you use G, and you use that to get the derivative. In the other case, you use an estimate of the derivatives to, you know, get the handle on G, and depending on, you know, which problem you're solving, one or the other will be more effective. That gives rise to a lot of really beautiful algorithms. Okay. Any questions conceptually on that? We'll prove those two lines on the next slide. Okay. So this is a big conceptual jump here. Remember that line well. Okay, good. So, now I know a lot of equations on that slide, but okay, good. So let's actually work out what happens here. So d theta of g of theta, right, is I want to take the derivative with respect to theta of the log of an integral of an exponential function. Oh my god, 3 horrible things in one. Okay, so let's tackle it, right? I mean, so the log, so it's just chain rule. So the log gives me in the denominator the value that was under the log, so this term here. Okay. And now I have to take the derivative of an integral. The good thing is, we already know what happens if you take the derivative of a sum. Well, it's the sum of the derivatives, right? The same thing can be done for integrals. You have to make sure everything is well defined. So if somebody doing, you know, real analysis is in the class, and they might stone me for being so lax on the math side here, but yeah, you need to prove that those things are actually well behaved. But assuming that they are, yes, you can just pull that derivative inside. Okay. Now, then, okay, so we apply it inside. Well, we have the exponential, so we apply, so we get the exponential back. Now we have the inner product, and well, everybody knows what the derivative of ax is. If I take the derivative with respect to x, it's a. And for an inner product, it's just one term, and the other one just goes away. Okay, so, well, what we get is the integral over e to the inner product between phi of x and theta times phi of x, and that the integral dx. Okay. Now, if you look at that, the denominator, now we have e to the g of theta lurking, right? That's exactly what we have by definition. This thing is the same as that one. That's g of theta. So now I can just pull that back into the exponential here, because it doesn't really depend on that integrand. And so I have dx of phi of x e to that expression, which was exactly our p of x given theta that we started with. So in other words, this is the expected value of phi of x. So you probably want to redo that derivation once at home just to make sure you're comfortable with it. I think that's useful in general. And well, then you do the same thing for the second derivative. Well, we just start with d theta already. I don't want to take it twice explicitly. Okay, good. So what is it? D theta of dx phi of x e to the phi of x theta minus g of theta. Now we just, apply to the exponential. So we have these two terms. We already know what we're getting here, because we just proved that. We proved that this is the expectation of phi of x. And so what I get is I get the first term, which is basically the expectation of phi of x transposed. And then here we have minus the expectation of phi of x times, because that doesn't really depend here on x anymore, the expected value of this term here, which is this one here. So we're home. Actually, I've probably written the transpose here. And we all know that this is covariance. It turns out you can keep on playing this game and you get the higher order cumulants out of it. So that's why this is sometimes called the cumulant generating function. It's also referred to as the log partition function. So if you're a physicist and you've done thermodynamics, you might have heard about this partition function. You might have heard about, energy, free energy and entropy and all those bizarre transformations between them that, at least to me when I took it, never made any sense. Maybe they make sense to you, but it didn't make so much sense to me. These looked like completely willful transformations. Turns out that those transformations are actually going from a convex function to the dual of that function. We won't be doing a lot of convex duality in this class, but if you ever want to make sense out of your physics notes again, look at convex duality and all of a sudden it'll actually look reasonable. So, more to the point, this function g actually turns out to be the Fenchel-Legendre dual of the entropy. And if you know this, you can actually write a nice paper about an efficient algorithm. Okay. So, let's look at some examples. We've probably seen all of those before. We've seen a binomial. We've seen a discrete distribution over x events. We've seen, a Gaussian. We've seen a Poisson. And then there are all those other weird things like Dirichlet, beta, gamma, and Wishart. And we'll get to them in a moment. So we've seen the Gaussian. We've seen what the Poisson looks like. If not, look at that picture on Wikipedia. It's a beta distribution. Dirichlet's. So in other words, there's actually a large stable of different, functions that, give reasonable estimates for distributions. And so if you need to model a distribution, you should probably check whether one of the distributions from the exponential families might not be a good fit to it. Why? Because if you have that, it just makes your life so much easier in terms of implementing things. And also with virtual certainty, some poor soul will have already written a very efficient piece of code to do inference with it, so you don't have to do it yourself. So make your life easy by at least checking whether one of those things fits. So what I basically showed you so far is, we have this exponential parameterization, covers a large range of distributions, and then, the log partition function gives us means, variance, and so on. And yes, you should probably be able to compute that derivation at some point. Now let's do inference. By the way, were there any more questions here?
So what will probability does not belong to the exponential family?
So what do probability, good question. So first of all, there are actually interesting proofs that if you just make your phi of x rich enough, you can cover everything. Okay. Now, covering everything means, well, you have to go to all sorts of nonlinear function spaces. But there are a lot of distributions that are not easily dealable with that. So for instance, Cauchy distributions don't give you all the nice machinery that easily. But they have some other nice properties. They're called stable distributions. And you can actually do a lot of the graphical models inference that you can do for Gaussian Markov-Random fields for this class of stable distributions. There's a nice paper by Bixson and Gestrin on that very issue. a lot of things in computational finance may not be particularly nicely amenable to exponential families. There people use what's called copular models. And these models have other nice properties. Basically there, when you do inference, you first try to match the marginal distributions for the univariate marginals to, and then you get essentially a distribution now over the where each of the coordinates comes from a CDF, cumulative distribution function. So you have basically vectors of random variables, which in their marginals are all uniformly distributed and have the range between 0 and 1. And then afterwards, you're just left with modeling explicitly the correlations. This is what people in computational finance do a lot. And if you then wonder, why could this have gone so badly wrong in 2008? There's a very nice story that basically they didn't really model multi-term correlations terribly well. So they only looked at pairwise correlations. So they didn't model that everything could go wrong at some point. And that's basically why things failed, because they were way too optimistic in their risk modeling. I hope it's been fixed since. Now, okay, I don't know. So let's use those exponential families. So the first thing that you would want to do is you'd want to compute, just the maximum likelihood estimate. So the negative log likelihood of p of x given theta is, assuming that these are all drawn independently, identically from the same guy, right? It's all the p of xi given theta. And now, by just taking the log of the exponential, so this becomes really nice. We have g of theta minus phi of xi and theta, sum over I going from 1 to n. Okay. So then, by the way, m equals n. Type on the slide. So let's take derivatives. So now we know what the derivative of g of theta is, right? That's exactly the mean. And this, if you divide by m and multiply by n, gives you the empirical average. So in other words, and we know that for maximum likelihood estimate this derivative needs to vanish. So what we therefore get is that the empirical average needs to match the expectation of that distribution. And you've done that 100 times already in the past. So for instance, if you were to toss a coin, right, and you toss a coin 10 times and it comes up heads 4 times, you say, well, I estimate that the probability of heads is 0.4. Right? Or, you take some random variables and you estimate their mean and covariance. And then you fit a Gaussian to it, and you say, well, this Gaussian has, a mean of 0.05 and a covariance of something. Now, is that really true? Well, of course it isn't, because, well, you just had a finite sample. But at least it's not a bad thing to start with. So, this is how you basically can show that the empirical mean and the expectation for that distribution have to match. Okay. Does anybody have problems with that slide? This is one of those other fairly fundamental slides. Okay. So let's look at a couple of examples. Well, what's the simplest thing? We have observations 0 and 1. Just to mix it up, I've picked 0 and 1 rather than minus 1 and 1. And so in this case, phi of x, well, let's just pick x. So in that case, the log partition function is just, e to the 0 times theta, which is 1, plus e to the theta, which is e to the theta. So the log thereof is our log partition function. So then we take derivatives. And the only expression, shorthand that I've used is I've used m1 to be the number of 1s and m0 to be the number of 0s. And so, well, of course, the expected value of that, the empirical average of that is m1 over m. Then by just solving for theta, So you just flip it over, subtract 1 from it, take the log, you get this. So basically theta is the log of the ratio between the number of times a 1 and a 0 occurs. Okay. Can this go wrong? Can you construct some sequence of observations for me where this goes badly wrong? Anybody? What's a good strategy? What observations would I have to have for this to go wrong? A single observation would automatically screw us, right? Because then we have essentially, M1 being 1 and M0 being 0. More generally, observations only of one kind will screw us. Because I have division by 0, or I have the log of 0. Well, so I have a problem. So what happens is basically, and this is an interesting property of the exponential family, that in many cases the boundaries of all the distributions that you can look at are not within the set of that family. So the boundary of all outcomes between is going to be exactly the probability that it always happens or the probability that it never happens. And those boundaries are not in the set. But that's often a good thing because otherwise, you would have a lot of trouble making sure that your solution stays within that domain. So these logs actually act as a natural barrier to keep you well controlled, and they are efficient mechanisms to ensure that also statistically. And I'll show you that. Multinomial. So you have observations between 1 and k. Sufficient statistic is Ex, so if I have k dimensions, then E sub x is the x unit vector in k-dimensional space. And so the inner product between theta and E sub x is just, it goes and picks out the x coordinate. Right? Then I take the log partition function thereof. Well, that's just the log of the sum of those terms. And you've probably seen this before, right? This is the softmax. Softmax because, well, if it'll be, so will it be greater, equal, or less equal than the largest term? So if I take this function here, is it going to be greater or equal than the maximum over all the theta i's, or less equal than the maximum of those? Who votes for greater? Who votes for less? Okay, the rest please wake up. So let's have the vote again. Now I want to see all arms. Okay, who votes for greater? Who votes for less? Okay, and the majority has it wrong. So here's why. And this is actually an important thing to help you also computationally. So we have log of the sum over I e to the theta I. Now let's, without loss of generality, assume that theta 1 is the largest guy. Okay. So I can write this as the log of sum over I e to the theta 1 times e to the theta I minus theta 1. Right? It's the same thing. I've just multiplied and divided. Which is nothing else than theta 1 plus the sum plus the log of the sum of e to the theta I minus theta 1. And I could actually expand that into 1 plus the sum I going from 2 to n e to the theta I minus theta 1. So now, what you can clearly see is, well, the log of 1 is 0, right? Log is a monotonically increasing function. We know that this is always greater or equal than 0. So we know that this entire expression here is greater or equal than theta 1. So it's greater or equal. Okay. So why did I go through this entire tedious derivation for you? Because in many cases when you're dealing with probabilities, you will be multiplying and dividing probabilities, and you'll be taking logs and exponentiating and all that. And the problem is that as soon as you take a really small or really large number and you exponentiate it, really bad things will happen, because this is how computers store floating point numbers. They have a mantissa and they have an exponent. Who's never heard of mantissa and exponent before? Okay. So basically what a computer does is it doesn't store a number as, that infinite dimensional, real number, but it basically does something like, 1.923 da 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 da. It uses a certain number of bits for that times, and then it uses maybe 10 to the 22.3. Right. It uses a certain number of bits for this part. And it uses fewer bits for this. This is called the exponent. And this is called a mantissa. And this is like the cool thing when floating point processors were invented rather than fixed point processors, where basically the floating point allowed you to not have to worry about the precision that you stored specifically in the mantissa. So if you have 64 bits, then you might be allocating something like 40 bits here. You might be allocating something like, 22 bit there. And then 1 bit goes away for the sign and 1 bit does something else. So what really happens here is that you have a lot less precision in the exponent than you had in the mantissa, about half the precision. So now once you go and exponentiate things, you move everything from here to there, and now any addition that you would have done on the log probabilities becomes a multiplication, which turns into a summation in the exponent, which makes it so much more likely that you will outrun that precision, because 22-bit isn't much, right? That's basically about 4 million. It's a fairly small number by, if you multiply a lot of things together. Are you looking for? So there's somebody in the back. Okay. Okay, fine. But actually, we're pretty much out of time anyway. So just to get that point here across, if you have different, if you have floating point numbers and you multiply them, and these numbers are really large or really small, then afterwards you'll have to take a log again. Never implement this. Always implement that. So basically go and pick the largest element, pull it out separately. This is really bad. This is good. And then apply the log sum to the remaining terms. This is numerically a lot more stable. In other words, when dealing with probabilities, avoid ever explicitly storing probabilities, always deal with log probabilities. Okay, and I guess we'll be doing the Poisson and so on and the conjugates in 2 weeks' time, or actually after the midterm break. So good luck for the exam.
Do you have any question about midterm? So everything is clear?